Okay. Um, thank you for having me. Apologize for ambient noise. There isn't a better place for me to be sitting. But uh, so I'm going to speak about how we measure various capabilities, um, and how we should try to think about differentiating between generic capabilities and safety. I'll try and keep this to around 30 minutes or so, maybe 40. So I'll start by talking about benchmarks and the idea of evaluations in the first place for advanced AI systems. And then I'll speak about some concrete ones that are currently of interest. And then thereafter, I'll speak about differentiating between safety and capabilities. So first, speaking about just benchmark and evals at a high level, what do we want out of benchmarks and evals? Well, maybe we want some measurement of how alignable are they. And, there's many things you could shoot for there. Like you would want to look at deception. You would want to look at, is there some misalignment that emerges? Maybe you want to measure that phenomenon. Let's say you're interested in intelligence. Well, there are many things that go into intelligence, such as reasoning, planning, creativity, memory, how factual or truthful something is. So there's a lot of words in these clusters, and what I'm trying to get at with all these words is that um, often in measuring these, you have to take an abstract phenomenon and then you have to make it very concrete. And some of these things are actually not quite the tree to bark up. So for instance, like creativity, there's not actually a creativity benchmark. And maybe that's because it just kind of came for free with a lot of other types of capabilities. So if you tried isolating that dimension, if you really tried concretizing it, you wouldn't actually be robustly measuring a phenomena that's distinct from the other ones. What I'm getting at is that there's a bit of a philosophical bottleneck where you're needing to think about these abstract words, how they fit in with others. Is a really clean distinction when you try and operationalize it with respect to these other concepts that are already measured, and so on. So it's actually it can be quite a difficult process to do benchmarking. There are other things you may be interested in, such as, can it be used as a cyber weapon? Can it be used as a chemical, biological, radiological, or nuclear weapon? That's a CBRN thing there. There are other things you may want to measure too, like its societal impacts. Maybe you want to measure how interpretable a model is. How would you measure that? So there's a lot of goals, but there are very few actual benchmarks, because a lot of these goals are actually not that distinct from other things, or they're not that measurable in the first place, or they come for free with other capabilities. So so I'm just trying to make it confusing. Now I'll try and articulate some things that you might want out of your benchmark, some specific properties to make sure that it actually is something that stands the test of time that people find useful. So one thing for benchmarks these days is you want a story for how this benchmark can scale beyond human level intelligence, or at least average human levels of intelligence. If the benchmark caps out at average human level intelligence, then it probably will not survive as a test for very long, because when you measure it, people will be able to, if you're able to measure this average human capability and collect many examples, other people could probably collect 10x more training examples than you, and they might it might be fairly straightforward just to fine tune a model to do that. So I think often these human level evaluations have a very short shelf life. So it's useful to think about what are some metrics that could get to expert level, a world-class level, or superhuman level. Another very important property is automatic evaluatability. So if you don't have automatic evaluatability, then you don't have fast feedback loops. To have automatic evaluatability, you can't have humans in the loop. You cannot have some system that says, I know it when I see it. If you have humans just say, I'll know it when I see it, when it's doing the right thing, then you have done almost nothing to concretize the phenomenon you're trying to measure. So I think a lot of benchmarking, the reason why it's not just a matter of collecting a data set is because a question well put is half solved. And your job as a benchmark creator is to put the question well in a way that other people haven't put it, or to see a target that others are not seeing, to reference Schopenhauer. So it's, I think, actually quite difficult conceptually, and my guess is just that like most STEMmy people don't have the humanities background to do the job. um, uh, so there's or some sort of qualitative reasoning ability to do the job. There's the ease of setting up. This is important too, and this requires more technical understanding. Does it require specialized training or complicated software to actually run your benchmark? Say you created an autonomous driving benchmark, but then to use it, you needed to set up this complicated computer simulation that only runs on Windows with some DirectX 11 graphics thing involved, and you need some specific compiler. This sort of stuff will just create substantial barriers to entry, and people will not end up using it. So it needs to be very easy to set up. So I think if it's just like you put text into an LLM, out comes their answer, you record the accuracy, that makes it a lot easier. But if you're needing a very complicated environments, I suppose another example would be in mathematics benchmarks. Some of them would require using some complicated automatic proof verification library, which basically only like a small fraction of maths PhDs know how to use. So it just had such substantial barriers to entry. There's also reproducibility. So you probably want your benchmark being deterministic. You don't want it varying each day so that models can be compared to a model from a year ago. This is important for apples to apples comparisons, for organizations to compete with each other. They won't be able to compete with each other or show their superiority with respect to somebody else if everybody's using a different measuring stick, or if there's a lot of variability in the measuring stick. Maybe they just got lucky. And so it can't have a substantial stochasticity. I suppose another point about automatic evaluatability is that this is important because if you're wanting university researchers to use it, if they're going to use human evaluators, they're going to need IRB approval, at least in the US, which means they'll need to go through some ethics committee, and this is going to take like 6 months or something. Like the prof is going to have to be trained in IRB stuff, and there's just a lot more headache. So just that's another thing that'll substantially affect the ease of setting up. Oh, there are more properties. So some other properties would be, you want clear downstream implications. You don't want your property just to be reflecting something in a vacuum. So an improvement on your benchmark should mean an improvement on various downstream tasks of interest, or an improvement on your benchmark. A method that improves on your benchmark can be used to improve downstream performance, but just, you want some correlation between this upstream benchmark and these downstream type of things. You don't necessarily want to measure the downstream stuff directly, because the downstream stuff, to be maximally realistic, might end up having a lot of hairy details that researchers and others don't really want to deal with. That is to say, it may substantially reduce the ease of setting up if you make it very downstream. So for instance, I have a legal, or done 2 legal benchmarks, and people just don't know a lot of the law stuff with it, and they're very long contracts, and it's just, there's some problem specific difficulties, like that the labels are some classes are very represented, other classes only have a few examples for them, and there's just some of these problems that compound that make it more difficult to use when it's very downstream. So often you're wanting something a little idealized as a benchmark, and not directly reflecting some property in the world, or some economic implication. You want a proxy for that that's a bit idealized and cleaned up. Something else that's important is that the metric needs to be interpretable. So if you're doing something like log loss, if you're having things compete on log loss or cross entropy or these other machine learning type of terms, people don't know what that, you can't interpret that. What is the entropy, the cross entropy, it was 2.3 and now it's 2.2. Nobody knows what that means. But accuracy, if you're saying the accuracy increased from, 70% to 80%, okay, I can understand what that means. So it's important to use very clear, simple metrics. I think a lot of more mathematically sophisticated people often opt for these more complicated things, but then it just becomes a lot less meaningful to people. And then another thing you need in your benchmarks is that it needs to be useful for hill climbing on or doing small local improvements to. So that is to say, you you don't want your benchmark being all or nothing. You either you passed or failed, and that's the only indicator. You want to score a continuous score that you got 37 out of 60. That's a lot more useful than some very steep step function. So for instance, like, did it make the app or not? um that'll be way too complicated. So you need to keep track of its intermediate progress. Otherwise, I think it'll be way too tough, and it won't be possible for people to come up with better methods to improve that system, or to improve performance on that benchmark. So, for instance, it needs to be there. A reason it needs to be continuous is often in machine learning, people will accumulate small little improvements. So you need to be able to discern whether the method had, 33% or 35%. That's relevant, because the progress of machine learning is often stacking on a lot of different improvements, or at least historically that was the case. So this is why it needs to be more continuous. Maybe I'll skip this. Well, I mean, or here, I'll mention, what are some possible ways that we could get to measure capabilities going forward that satisfy all these properties? One thing is in mathematics, and that would be like auto formalization or automated proof checking. That still probably is bad on the ease of setting up, but it at least has a lot of other things that it can scale beyond human level intelligence and all these other sorts of things. It can prove things that humans couldn't prove, but there's a sort of proof checker that can say whether it's correct or not. Another possible way of measuring this would be with games. So if you have AIs compete against each other, you can get some relative ranking of their performance. You could just keep throwing different games at them that they've never seen before, have them compete in it, see the relative ranking. That could get beyond human level quite understandably. There's also forecasting. Forecasting is where you're predicting the future. So like, who will win in the election? Will Nvidia's stock exceed $1,000 per share? Or when will it? These are questions about the future. And machine learning models could get very superhuman at this. Right now, it looks as though they're actually better than like nearly all experts and nearly everybody, but that you could imagine them just keep getting better and better at this. So this is another interesting benchmark where there's more automatic evaluatability. You basically train the model up to 2023 data. You show it questions for which the answers were determined inside of 2023, and you see its ability to predict the events in 2023, not having seen any of the data in 2023. So this is how one could set up some sort of forecasting benchmark. But anyway, this maybe gives a sense of some dimensions that people might end up pursuing as they try and measure general capabilities and make them increasingly intelligent. That's a bit forward looking. I'll speak about what people are doing now in measuring capabilities. I'll speak about 3 different benchmarks, which I created in 2021, 2022, and then one recently a week or 2 ago in this year. And I'll just like pause for like, I don't know, 5 seconds or something, because there's I'm a bit cognizant that there might be a bit of cognitive overload. So that's a little. Okay, so benchmarking for various capabilities. What are the big LLM providers doing about that? What are they using? And they'll use a variety of benchmarks. One of the ones they use is this thing called MMLU, which I think is probably the most downloaded data set on Hugging Face or so. But we introduced this some years ago, um, largely to measure how general the capabilities of models were and how far we are away from, very advanced systems that are polymaths or just know about everything. Um, or how suitable they could be as a sort of Google competitor. I think largely this was, when is Google going to open their war chest? And I thought whenever the MMLU is about like 70% or above, then Google is going to view LLMs as a threat to their search business. So this is largely why it was created, was to track that and predict when that would happen. And then of course that happened. So this is an example here, two example questions. Find LC in Z sub 3 such that Z sub 3 of X. It's the quotient group ring. I don't even remember. It's been such a long time since I've taken abstract algebra. Anyway, there's that answer. Here's maybe a more fun one from professional law. As Seller, which is an encyclopedia salesman, which we'll call Seller, approached the grounds on which Hermit's house was situated, he saw a sign that said, "No salesman. Trespassers will be prosecuted. Proceed at your own risk." Although Seller had not been invited to enter, he ignored the sign and drove up the driveway toward the house. As he rounded the curve, and a powerful explosive charge buried in the driveway exploded, and Seller was injured. Can Seller recover damages from Hermit for his injuries? So then there are multiple options. Yes, unless Hermit, when he planted the charge, intended only to deter, not harm intruders. Yes, if Hermit was responsible for the explosive charge under the driveway. No, because Seller ignored the sign, which warned him against proceeding further. Or no, if Hermit reasonably feared that intruders would come to harm him or his family. So this is a question from professional law inside of MMLU. The answer to this is B. Yes, if Hermit were responsible for the explosive charge under the driveway. I'll note that this is currently for LLMs among the toughest subjects, often the toughest subject, professional law. They may be getting something like 70% accuracy on these questions. These are questions from the bar exams with particular focus on, if I recall correctly, tort law and criminal law. So this gets at like, what's their ethical and legal understanding of things? A lot of other subjects are substantially easier, but such as even the abstract algebra one. But these are some other types of questions. There's some conceptual physics ones. But overall, we've got 57 different types of exams. So we've got some college mathematics exams. We've got physics. We've got econometrics. We've got law. We've got medicine. We've got computer programming. We've got computer programming at a collegiate level. We got computer programming at a high school level. We've got basically whatever exam you care about, it's likely in there. And so this is just sort of like a bundle of all the exams you'd care to give humans. And they're doing pretty well, pretty much all of them, which suggests that these are like, they're not omniscient with respect to publicly available knowledge, but they're close. And it wouldn't surprise me if like 4.5 is like basically knows everything there is to publicly know that is of, general interest. So let's see. Here were the results at the time. This was GPT-3 back in 2021. GPT-3 was, there's the smallest GPT-3 model and there's the largest. 25% is random chance accuracy. So you could see that it was basically at random chance, and then it became a lot higher. Other tasks like common sense understanding, like how quickly does butter melt? Or if I leave butter outside the fridge, will it melt or will it freeze? This is a common sense understanding question. It will melt. Linguistic knowledge was just, does it, can it tell me whether there's a grammatical error in things or things like that? So those were easy and the models could handle those, but only with the very largest GPT-3 model did this capability somewhat turn on, that it had the ability to answer these knowledge type of questions in the world. And these were the results at the time. Most were around random chance levels, except for this thing called unified QA, which was a big transformer, and GPT 3x large, which is a big transformer, but the rest of the models weren't doing very well. And here was I didn't share this figure at the time publicly, but privately is like, look, here's how performance is scaling. So if you have a transformer that's, got a few more orders of magnitude of compute thrown at it, then it's going to be pretty performant. So let's see. Yeah, that was so the thought was maybe 100 trillion parameters will give you an 85% average or so. But of course, we're not dealing with parameters now because of recent advancements. We can make the models a lot smaller, but you still need a lot of flops. But this is back in the day when we were approximating flops, or the amount of compute going into models with parameters. But anyway, things have been scaling nicely since then. Here's where we are now, some years later. This is what things looked like then. And you could basically see that, like, yeah, we'll have a very powerful transformer, in the future that'll be pretty broadly accurate and know a lot about everything, and answer things at a reasonable level of reliability. And if that's the case, then we should expect some type of like Google search competitor, or LLMs to serve as a Google search competitor, or Google 2.0, so to speak. So let's see. Here's where we are now. Here's the subject performance these days. We've got ourselves, medical genetics, marketing, all these are near 95% plus. It's, they're doing a great job. College biology. So it's, by the way, their capabilities are so weird. Look at high school biology and college biology. Barely a difference in performance between the two. One requires 4 years more learning, but there's not actually much of a sizable difference between the two. College biology is for entrance to PhD programs in biology and basically crushes it. And it also crushes high school biology. So they don't necessarily learn things in the way you'd expect. They've actually, back when a year ago, for instance, they were both at like 80%, which it's like, shouldn't it first know all the high school biology before it starts to learn the college biology? But no, that's not the case. So this just sort of shows how like knowledge doesn't actually stack in the same way with these models. This is GPT-4 with a calculator. If it's without a calculator, elementary mathematics, it will do very poorly on elementary mathematics, but it's doing just fine on elementary mathematics. It's all the way up here. But without a calculator, do much worse. But it can do college mathematics without much expertise in elementary mathematics. It's very, very interesting capability profile with these models. But as we can see, there's a lot of other subjects one might care about: business ethics, high school statistics, college physics. So college physics, this is a difficult exam. This is basically the exam to PhD programs in physics, and it's getting 83% accuracy or so. Very impressive. But we can see that professional law is very low. It says that virology is low. This is a fabrication. I think OpenAI just specifically made it like refuse some of those questions or something. But if you give it other related virology questions, it will answer those and get very high performance. So I think that there's a bit of like gaming here to seem responsible, but you can show it other virology questions and it'll answer them just fine. So I think that I wouldn't read too much into that. So instead, do professional law, econometrics, these other sorts of STEMmy topics are harder, but some, that professional law, though, is still also very difficult, in addition to STEMmy stuff. So that's where the results are now. And we'll see in the summer what the overall accuracy is. Maybe it'll get 92% accuracy or so. I think that basically MLU's maybe got a year or two left of life in it. I don't think it's saturated, because I think that there's a lot of white space. You can see, like, here's the bar, and then to the right of it is white space. There's still a lot of white space left between that and the rightmost or the right black bar. So I think you could easily get to 95% plus accuracy, and then I think you're starting to run into like the limits of the tests. But the tests are generally very well curated. So we created it largely just by copy pasting a lot of questions. So I mentioned that there was a lot of difficulty in some of these STEM-y topics, STEM and logic type of topics. So this prompted me then to zoom in. Let's try and get a better measurement of STEM performance. So then we created the math data set, which is a data set of 12,500 competition mathematics problems. And we can see there's some other data sets. There's this meta math one. There's this deep mind math one. We created this math data set. I blanked out a solution to a problem. So I'm going to read the problem just so you can get a sense of the difficulty of some of these questions. So Tom has a red marble, a green marble, a blue marble, and 3 identical yellow marbles. How many different groups of 2 marbles can Tom choose? So let me think about that myself. So the solution is there are 2 cases. Either Tom chooses 2 yellow marbles, in which case the group looks the same, or he chooses 2 marbles of different colors, and there are 4 different colors. So the total number of distinct pairs of marbles Tom can choose is 1 + 6 = 7. Okay. Anyway, requires some thinking. But that's largely what this data set's trying to test. And at the time of release, the models are getting, around 5% accuracy on these. They have to write out the correct answer. They put their answer in a box to indicate what the final answer is. They can use a scratch pad, but then they need to say this is the final answer. And it was a lot harder than other mathematics data sets. But that was back in the day. It was 5%, and we thought, maybe this means deep learning models just can't reason or something like that. Reasoning, that although they can get knowledge and all that sort of stuff, for them to do this multi-step reasoning, this will, hitting the limits of deep learning, hitting the limits of language models. What are we going to do? But yeah, basically all you need to do is just scale up the models. And where we are now is that the models are around 50% or so accuracy. And as I gather that next month will be a sizable advance in the reasoning abilities of models, such that at least some people I speak to who work on this in industry think that maybe we'll solve the International Mathematical Olympiad in a year's time. So anyway, making a lot of progress on this math stuff. For reference, I got, if you give me 20 questions for math and give me an hour, I think I got 75% accuracy. And then a 3-time International Mathematical Olympiad gold medalist got like 90% accuracy on it. A PhD student in AI and computer science who doesn't particularly like mathematics got I think 40% accuracy. So anyway, hopefully that gives a sense of the range of how people can perform on this. Okay, so I just discussed 2 data sets, the main ones that people do for general knowledge, and then this like more difficult reasoning type of stuff. And now I'm going to talk about a more safety relevant capability, which is which are capabilities that enable these models to be sort of dual use. So the White House executive order, so basically the Biden White House put out an executive order saying, if you need AI labs, you need to look for whether your models can be used to create a chemical, biological, radiological, or nuclear weapon, and you need to also check if they can do things like be used for cyber attacks. So there's a concern about malicious use from these. A lot of these capabilities can be used for good and bad. You might want your model knowing how to be used for science. Science is good, according to the according to scientists. But or people with scientific orientations. But it could also, that same ability can be used for expert level virology, which can help you make a bioweapon. We want our models to be more better at coding, but then that can be used for finding vulnerabilities and launching cyber attacks. We want our models to be more empathetic, but that can make them more persuasive. We want our models generating interesting visual content for us, but then that can be used for deepfakes. So this makes safety a fairly difficult issue, that the good is tied up in the bad to some extent. So one possibility is maybe we can focus on some of the capabilities that are particularly hazardous and just sort of delete those from the models while preserving the rest of the capabilities. So I said we wanted AI for science. Maybe we can delete the expert level virology knowledge inside of the model, and we can keep all the other knowledge about science. So that's an idea. That's the idea of machine unlearning. And recently, I suppose you could check out WMDP is the acronym for this, WMDP.ai, to access the paper. We collected around 4,000 multiple choice questions to measure whether a model has hazardous knowledge or proxies that serve as a measure of hazardous knowledge in biosecurity, cybersecurity, and chemical security. We didn't include radiological and nuclear weapons because that sort of relevant data is called restricted data, which you can't publicly proliferate. So hence we didn't focus on radiological or nuclear. But the idea is there's some basic knowledge, like general biology. There's expert level virology. And inside of expert level virology, there's the ability to make bioweapons. Now, we can't release a data set of cookbooks for smallpox and see whether a model like says, oh, yeah, I know about that. But what we can do is we can test for various things that expert level virologists know, and we can try to remove that knowledge while still preserving the general biology knowledge. Likewise, in cybersecurity, there's general computer security, like knowing like what two-factor authentication is, or that ransomware is bad. But then there's more specific capabilities, like can it reverse engineer code? And then there's the specifically hazardous stuff of here are instructions for how you do a cyber attack on a power grid. So we can't create a data set of the red stuff, but we can create a data set of the yellow stuff. And we can try and remove the yellow stuff so as to remove the red stuff by extension and preserve the green stuff. So that's the basic idea. Speaking about this more relatedly, or in more concretely, the data set has various precursors. So we could try and get rid of some knowledge about enhanced potential pandemic pathogens, or we could have neighbors of ideas in concept space, and try and remove those. Or if there are specific steps in a cyber attack, we could see whether we could try and remove knowledge that would be essential for having it pull off that cyber attack. For instance, it's got to do an API call to this hacking tool. Well, let's just delete knowledge about that hacking tool. Those are some of the ways in which we'll come up with proxies for the scary stuff without specifically identifying or revealing a lot of the directly scary stuff, or stuff that could really enable some let's say terrorists or random disgruntled actors to cause a lot of damage. So this is this proxy idea for how we can study this sort of stuff in the open as a broader intellectual community. Okay, so some design choices we made for WMDP are, we had 4-way multiple choice questions. They're written by academics and technical consultants in biosecurity, cybersecurity, and chemistry. These questions were generated in view of various threat models of if you were trying to create a bioweapon, what would be useful knowledge for that? And then let's try and remove things related to that knowledge. Here's a sort of biosecurity threat model. They come with an idea, they design something, they build it, they test it. Maybe it doesn't exactly work, so they, tinker their design, and then they ultimately, release it in the public. And for cyber attack, the threat model is they gain reconnaissance, they collect background information. Oh, they're using these servers. Oh, they're using this version of the software. And then they identify vulnerabilities like, well, that version of the software has this exploit. And then they exploit that exploit, and then they do malicious stuff while inside. That's sort of the stages of the cyber attack. So I was mentioning what we want to do is we want to delete that yellow stuff to also by extension delete that red stuff. But to do that, we need basically something called unlearning. And this really wasn't, there weren't really any techniques for doing that. So we kind of had to create our own. There's unlearning techniques for deleting specific examples, but not for deleting entire, breadth of knowledge. Unlearning historically was just for deleting information about a specific user to comply with GDPR requirements, but not delete an entire area of knowledge in a model. And so people were wondering whether this can be done or not, but it looks like you can. Here's a kind of a complicated diagram. The idea is there are two terms. There's a forget term and a retain term. The forget term tries to make the model have a more novice-like representation. So you tell the model, think as though you're a novice when you're processing this text. And then you tell the model, think as though you're an expert in virology when you're processing this text. And you want to find the difference between those two thought activity patterns to sort of point in the direction of like, this is what more novice-like thinking is like. And then you say, model, think more like the novice. And you adjust its representations in that way. But then there's this other term of retain, which is like, but when you are adjusting yourself to think more like a novice, don't try and like, don't go overboard, or don't try and forget some other generic knowledge that you should have. Like, don't over adjust to that objective. So there's a bit of a balancing thing of like, forget this specific virology stuff, but remember all this other sort of stuff is what the retain thing is doing. And it looks like this works fairly well. So there's a base model, and then there's a model that uses cut, and there's random chance accuracy. As we can see, the MMLU from before is largely the same, slightly worse, but the amount of knowledge in the models is about hazardous stuff like bio and cyber is substantially less. So it looks like it basically can work pretty well. We'll update the paper in a week or so to hopefully make the MMLU performance drop be even smaller. So that way it can be used in production since we were so close. Compared to other unlearning methods, there are some other unlearning methods that just basically don't work. Like ours is like basically the only game in town. Sorry to say. That said, we're not done with unlearning. I just mentioned the MMLU performance drop is still like noticeable. It's not huge, but it's noticeable, which still isn't relevant for industry. And if we zoom into specific subjects like introductory virology, it actually deletes introductory virology. So it deleted a bit too much. So while college biology knowledge is still the same, specific virology stuff got ruined in this unlearning process. So we would like the introductory virology performance to be the same as it was before. So it still isn't as it should be. We'd like to more precisely excise the information. Is the information actually removed? That's a possible question. Well, we did some tests, like we could train a linear classifier or a multi-layered perceptron or some sort of model on top of each layer and try and extract from that layer information to predict those WMDP questions to test for that hazardous knowledge. And they just basically can't after you unlearn it. So if you try and find the information inside of individual layers, you just can't, which is evidence that it's actually removed. It's not just being hidden somewhere. We train machine learning models to extract it from the model and they can't find it. And likewise, if you create an adversarial attack to try and, adversarial attacks can bend models to do arbitrary things, if they can get them to spill the beans and coax them to say whatever. But if you actually try to use it to for the unlearned model, it's not able to it's not able to generate the the knowledge or generate the answer to advanced virology type of questions. In both cases, it just produces gibberish, whether there's an adversarial attack or not. So it just doesn't answer. And then finally, it's worth mentioning that the questions are relevant for actually hazardous knowledge. So we were using proxies of hazardous knowledge, but we collected a data set of actually hazardous stuff that we'd get in trouble for releasing. And the method, the unlearned model also didn't have the knowledge for how to answer those sorts of things correctly. Yes.